Yeah, I think so.
Okay, wait, can you enable screen sharing? I don't see it. Or it's not letting me.
What happened?
I think there's a button to like enable screen sharing for
Oh,
yeah.
Advanced options, all participants. There you go.
Cool. Yep. This works now. Share. Okay, people can see this, right?
Yeah, you might have to repeat this.
Yeah, I'll go back to the start. Can you see it now? It doesn't say like no
Yeah,
full screen or anything, right?
Yeah, we're good now.
Okay, cool. Yeah, so I'll just start from the top. All right. Yeah, so this is my work, offline RL for natural language generation with implicit language Q-learning with some people at Berkeley. How this talk will probably be structured, since some of you are probably like NLP folks and others of you do more like maybe RL focused stuff. I'm probably going to start from like basic foundational RL concepts, giving some background, and then building up to sort of like motivate implicit language Q-learning, why offline RL is interesting and useful for language tasks and this sort of thing. So the first half of the talk will be sort of that background and motivation, and then the second half will be more about the method proposed in my paper. Hopefully that's a good setup for most people. Yeah, so I'll get started. So we can start by thinking about like how we would train like a large unsupervised, or how we'd get a large unsupervised language model to do something like a dialogue task. Like you have a customer service bot and you want it to like sell customers products and make them happy. You could, give the language model the dialogue history and, query it for response, but it might not always do exactly what you want. Some of the time it might respond with, good responses, and other times it might do something you really don't want, like be rude to your customer, because, it's not optimized for this task. Of course, we can kind of fix this by adding a little prompt and maybe it does what we want, but there's not any like too strong of guarantees here. These prompts can be the model can be a bit brittle with respect to these prompts, and it might do something unpredictable. So ideally, if we want to get our language models to do a task, we need some better optimization method. And a more typical approach is you collect some data set of your task. Maybe you filter the data set a little bit for the kinds of interactions you really want, and then you just fine tune the model on that data, and that should get you a model that's like better at that task that you want or whatever. In this talk, we'll refer to this as like filtered fine tuning, or %BC, which is sort of the RL term, which is like filtered behavior cloning. And behavior cloning, or just normal fine tuning, would refer to like not doing like a filtering step. Maybe you just collect data and you're not filtering it for like the positive interactions or something. So that's sort of a common approach and very straightforward and easy and pretty reliable way to do this. But we still have to like filter the data, and for more like nuanced behaviors that we might want our model to optimize for, it might be kind of hard to do this. Like say we wanted to optimize our customer service bot for efficiency, like completing the dialogue task as quickly as possible. It's not clear that like filtering the data for like the shortest interactions and then doing supervised learning is going to give you that maximally efficient bot. This sort of idea of filtering and fine tuning doesn't solve every case we want, and ideally we'd want a method that is able to handle all these cases. So that motivates this question of like, why not just try to optimize the model directly for the thing we care about? So like what I mean by this is, you can take the data set, apply a utility or reward function to it, and then run some RL procedure, and you get out a model that's directly optimized for the thing you want. Of course, this is ignoring, the challenges with, maybe defining a reward function might be kind of hard, but just assume for now that we have a good reward function. If, we have this, it would obviously be better to just directly optimize for that. But so that's sort of the premise of this talk, is basically like why not use this offline RL? And we're going to sort of discuss like why offline RL is a good idea, and what sort of makes it different from, the online RL sort of approaches that you might be familiar with, like the PPO stuff OpenAI does and whatnot. And yeah, so, obviously RL has a lot of complicated topics, and some of you might be from NLP backgrounds, as I mentioned. So we'll, sort of we're going to sort of step through the RL concepts and build up the necessary background in the first part of this talk. Okay, so we're going to start by sort of defining like how language model interaction might work, look like in an RL setting. So, we know how, language generation works. What does it look like in, an RL environment? So we might start with, like some initial token, and then our agent's supposed to take an action, which is the next token in its utterance. So we'll say hi, selecting a token, and then it appends that token to its history. And so the agent's observation is all the previous tokens in the dialogue. And then it takes picks another token as its next action, and it keeps doing this until it finishes its utterance in, say, a dialogue setting. Once it finishes its utterance, it outputs like a special end of action token, which signals to the environment that we're done with our turn and we are ready to like receive a response from, another person in the dialogue. And then, we get back a response from the other person, which sort of, before we were just going token by token, and then we get a bunch of tokens back and we skip forward, and that gets appended to our history. We also get a reward back from the environment for our action. And then we take, we do this again where we select, the next token in our response, and we keep doing this until, we keep doing this. We respond again, and this is sort of like an iterative process that repeats where we say things and then we get a response back from another person, and we're going to sort of do this until we reach some termination condition. And in the RL world, this sort of process would be called a partially observable Markov decision process. So that's sort of the setting that we're in here. And one thing to note is that this is sort of critically different than like the like learning from human feedback work that some of you might be familiar with from OpenAI, in that there is actually an interactive process. So in like OpenAI's work, the reason I can use something like PPO effectively is because there's no interaction. What they're doing is you have a prompt and you're generating a response, and then you get a reward. There's no like interactive process that you're optimizing over for, where like you generate some text and then you get back more text and you generate some text. So this sort of interactive setting is useful in, say, like a dialogue where you have a bot that's trying to like bargain for the lowest price in a dialogue, and there's this whole dialogue that you want to optimize over. There could also be like, say, a coding model in your IDE, and it's interacting with you turn by turn. You're editing, it's editing, and you could just optimize it to make good single completions, or you could optimize the whole interactive process for like a successful bit of code, a successful outcome.
Charlie, if you could just leave the Discord fourth channel, because it seems to be pinging.
Sorry about that. Quitting Discord. Okay, it should be good now.
Okay.
Yep. Yeah. Oh, and also if there are any questions, like you can speak up. We can be interactive if you want. So that's sort of the critical difference between the setting and like, some of the other settings you might be familiar with. And that's sort of, we'll get to this, that's sort of why offline RL specifically is a good idea versus some of these online RL approaches that you might be familiar with. Okay, so just to recap what we talked about, we have an agent that learns a policy that predicts the next token and our utterances. Then the environment's going to respond to us with, a new utterance once we finish our turn. And then we also get a reward function back. So now that we've sort of defined the setting that we're in, we'll look at like, how do we learn these agents to optimize this? In reinforcement learning, our goal is, to maximize the expected utility. learning the policy to maximize the expected utility. And this is typically done through sort of a trial and error iterative learning process where, what this means is we take our policy, we go out and interact in the environment, we give back some interaction data, and then we update our model. So this is a pretty complicated process where you're actually going out into the environment, interacting and updating our model. This is as opposed to supervised learning where you just have a data set and you're learning from the data set. There's a lot more going on in RL. And this is why it's, so data intensive and like systems complex is because you have all this interaction and exploration you have to do. Offline RL is different from, standard reinforcement learning in that, our goal is the same. We're still trying to learn the policy to maximize the reward, but we impose this additional constraint, which is that we can only learn from a static data set of interactions and rewards collected by some potentially suboptimal behavior policy. What this means in practice is we're not allowed to interact with the environment. So this behavior policy is just the distribution of the data set, as you would call it in supervised learning, where we have some static data set and we're supposed to learn the best policy we can from it without going out into the environment and interacting with it. This is makes it a much harder problem than standard online RL. So like the example that Sergey likes to give is, imagine you have a agent that's supposed to be controlling your like heating system in your house or something, and maybe all your you give it like all of this past data of like your heating system, and there's sort of a trend of like in the winter you like the house to be warmer. An online RL agent might, observe this pattern and be like, oh, maybe it's a good idea to turn the temperature up to 200. There's a trend here. It goes out and tries it. It learns that's a bad idea, and it comes back to you, and it updates. It learns from this. Whereas in offline RL, we're not allowed to do this. So we have to be able to like know what is a good and bad idea in these sort of weird counterfactual settings. That's sort of why it's a challenging problem. So that's the definition of offline RL. And now that we've sort of defined the problem, we can sort of look at like why this is a good idea for lots of language tasks, and what sort of the challenges here are in the offline RL space. So we're going to walk through, in our paper, we set up these like 5 conditions for like a practical offline RL algorithm. And I'll sort of walk through each of these and we'll see like why offline RL is a good idea for language tasks. So the 5 conditions are: 1, easy to use. Ideally, we want our method to be, easy for people to use. It's less likely that your method will take off if it's really hard for people to get working, especially when we're talking about like large scale language models where we can't train these things a bunch. Oh, I see a hand up. Shablad, I hope I didn't mispronounce. Do you have a question? No? Yes? Did you accidentally push the button?
I think he's posting in chat.
Oh, he's posting in chat. Okay, I didn't have that chat pulled up. Yep, just type your question.
Hello.
Hello. So you said in offline RL, you train the policy, then have it play again to collect the next round of data, right? In theory, we do it as in the theoretical setup is just a one-time thing. In practice, there is like, you'd probably do this iterative setup, and there's actually a project I'm helping with that's looking at this. So like, ideally you train your offline RL policy on some data, you deploy it in the world, you get more data, and then you fix it up with the new data, you improve it. But yeah, you can do this, and in practice is what people do. The theoretical setup of offline RL is no, you don't get to try again. Yeah. So DQN is online RL. That is different, and I'll talk about that a bit. Yeah. Yep. Yeah, so we'll talk about this stuff like DQN. So the methods for offline RL are a bit different. There's like some things in online RL don't work in the offline setting, and you have to do a few things differently. Yep. Okay, so yeah, let's go through these conditions. So easy to use.
There was one more question.
Oh, there's another question.
Parth
Parth?
Shah.
Yep.
Yeah, hi. So this this table that I see on the screen right now, it says online RL is not practical in interactive settings. That seems like a bit counterintuitive. Can you?
I'm gonna get there. Yes, well, I'm gonna get there. We'll get there. That's one of the main points of why offline RL is useful here. So I'll definitely get to that. All right.
Okay,
I'll
thanks.
keep going, and yeah, I'll get to that. The answer to your question there. Yeah. So the first condition is like easy to use. So like obviously we want our method to be stable, straightforward, and easy to use, especially with like large language models where people don't really want to take risks with like unstable stuff. There's not much budget to do a ton of tuning on large models. So if you want your method to take off, it really needs to be pretty easy to use in the NLP world. The other condition is sort of like the definition of RL, like we discussed. Like it's ideal if we can just directly optimize for a utility function instead of like having to define desired behavior by like a data set or something. And then the other one is practical and interactive settings. And what this means is sort of the thing I defined earlier, which is like we want to optimize over these interactive processes. And we'll discuss like why online RL is not practical, at least for a lot of NLP settings in terms of these interactive settings. And then the next condition is able to leverage existing data. So, in NLP, a lot of the breakthroughs have come from methods that can just soak up all the data online. And ideally, we want a method from RL that can do this as well. And then the last one is sort of a highly technical offline RL term, which we'll get to. Temporal compositionality. I'll get to that shortly. Okay, so we'll go through these one by one. Obviously, supervised learning is highly stable and easy to use, straightforward to set up and implement. Like it just works most of the time. Same thing with filtered fine tuning. So remember, we defined this as just like supervised learning on filtered data. So of course, it's the same thing. Online RL usually, is very unstable with respect to hyperparameters. It exhibits instabilities often, and there's a lot of different moving components to juggle. So I would not call it easy to use, especially when like the random seed can be considered a hyperparameter. Offline RL, the answer is a bit more complicated. Sometimes it's easy to use. And so let me elaborate on this. So in the offline RL world, I would say that there's sort of two high-level classes of approaches. One is sort of this decision transformer approach, which is basically just supervised learning. So it's like reducing the offline RL problem to supervised learning and taking advantage of the stability of supervised learning to do some offline RL optimization. So of course, it's very stable and easy to use. The other like high-level approach is this value function learning kinds of methods, which have a lot more moving components. They look more like classic online RL methods, and they can involve a bit more tuning, and they're a little more like precarious to get working. So I would not call those as easy to use. The other condition, so the next condition, able to optimize user-specified rewards. So we discussed this a bit. Supervised learning is just maximizing the likelihood of the data. It's not, optimizing necessarily for the, utility function we might define. Filtered fine-tuning is like, it kind of does this. I mean, if you're filtering your data according to like, to satisfy the reward function that you're defining, then it's sort of optimizing the defined utility, but not exactly. I would give it a yellow circle. Online RL, of course, this is literally the definition of its objective is to optimize utility function. Same with offline RL. So now this is the one that Parth was asking about, practical and interactive settings. So we defined this interactive setting of like, I take a turn speaking, then I get a response back, and then I speak again, and there's this interactive process, and we're optimizing over the entire process. Of course, this is not a special case for supervised learning. You can literally just take, interactive data and maximize the likelihood, and it doesn't change anything. It works the same. Same thing with filtered fine tuning. It's the same thing. Online RL, on the other hand, like we discussed, you have this like trial and error interactive learning process. So like by definition, it's built to optimize these interactive settings, but it's not practical in them because at least in these like the NLP world, because like, imagine you're doing dialogue, the environment interaction corresponds to like actually going out and talking to real humans. And, having an agent go out and do this over and over again, iteratively, and, learning, its task by just talking to humans again and again is going to be time consuming and pretty expensive. It's, I mean, maybe if you're Google, you can get your bot to talk to a bunch of people, but in general, it's not, the most tractable approach. That's, why you don't see a lot of RL robots now, because, the robots actually have to interact with the world. So, learn through interaction. Of course, you could also build like, a really rich model of like human responses and optimize your bot against that. But like for complex enough, rich enough tasks, language tasks, like this probably isn't going to work. Like you might not be able to get, a rich enough model from the start. So that's sort of why I would say like online RL is not necessarily practical in interactive settings, at least for a lot of the problems in NLP that we might care about. Offline RL, on the other hand, like we've mentioned, literally removes this assumption of environment interaction. We can just take a data set of previous collected human dialogues and optimize over it. So yeah, it's more practical in this setting, and that's sort of the big thing that distinguishes these two. Parth, does that make sense?
Yes, that makes sense. Thank you.
Yeah.
So just to kind of pause here, because I think this is like an important point.
Yeah.
The claim is that online RL is impractical in the interactive setting because it's inefficient in terms of data collection.
Yeah, exactly. You have to like have your model repeatedly go out and talk to humans to optimize for a utility function. Yeah.
Okay.
Offline RL is sort of like a better data sponge, I guess. Yeah. Yeah, so like by definition, online RL does this like trial and error learning. That's the claim. Yep. Yeah, so the next condition is able to leverage existing data. This is maybe a bit similar to the last claim, but basically, there's a lot of data online of, past interactions, at least for NLP data. And a lot of, the big methods that are working, like unsupervised pre-training, are able to soak up all this data. So ideally, we'd want our offline RL method or our, whatever utility optimization method we have to be able to do this. So obviously, supervised learning and filtered fine-tuning can do this. Online RL, by definition, to some degree, you could probably mix some of the existing data in, but by definition, it needs to learn from its own interactions. So it's collecting new data in a sense to learn from, which, not super ideal. Offline RL, on the other hand, can of course just soak up any data set you give it. Now, the last big condition is temporal compositionality. And this is a offline RL sort of technical term, which refers to this like sort of the ability of like a utility optimization method to stitch together the good parts of suboptimal trajectories to find the optimal policy. So what this means is like, suppose you're in this maze setting and your data set has two trajectories, or this is a simplification, but a good example. So you have two trajectories. One is the path from A to B, and the other is the path from C to D. What you really want your agent to do is go from A to D, but there's no full optimal trajectory of this example in the data set. Some of the trajectories have the right ideas, but none of them have the full thing. Can you learn a policy which is able to stitch together all the good things in the data to find the optimal thing? That's what temporal compositionality refers to. And if you had like a supervised learning model, it might actually sometimes go from A to D, but most of the time it's probably going to go to from A to B. So it's not really able to do this. Whereas like, certain offline RL methods are actually able to figure out this sort of stitching thing. And it sort of just means that your method's more powerful optimizer, essentially. So, like I said, supervised learning is, maybe sometimes it can do this, but generally not. Same thing with filtered fine tuning. Online RL, it's a bit weird to put it consider it as temporal compositionality because, it's not learning from a static data set. It can go out and try things, but I'll give it the check mark because it's kind of able to arbitrarily optimize utility functions. Offline RL, the answer is a bit complicated and sometimes. So again, we'll go through like the two high-level approaches and see how they check out on this one. So the decision transformer style methods can sometimes do this, but they generate, so there's some like offline RL benchmarks which measure the ability to do temporal compositionality, and these kinds of methods kind of fail at this. So I would say that they are not able to do this kind of thing. Whereas the value function methods, this is where they shine. They can, do this really powerful, data set optimization of stitching. That's one of the big advantages. So looking at this, we see that like offline RL seems like a good idea because, it's practical for these interactive settings that we might care about. We're able to, soak up all of the existing, language data that we might have. We can optimize any utility function we give it, but there's sort of two big question marks. We have, sort of these like two approaches to offline RL. One is, easy to use, but not as powerful of a utility optimizer. The other is a bit harder to use and not as, more of a powerful utility optimizer. So, this is a bit of a dilemma. And this is sort of what we're looking at with our implicit language Q-learning paper. I think it's pretty important to have like a easy to use method, especially for NLP if you want your method to be scaled up. But you also don't really want to sacrifice the utility optimization power. So we tried to, implicit language Q-learning is sort of this value function based offline RL method. We tried to sort of minimize the need to tune parameters and the complexity of it a bit, as much as we could at least, to ideally turn these two orange circles into green checks. Right, so now so that sort of completes the first half of the talk where I'm sort of motivating all these ideas. Now we're gonna kind of get into like what the actual method of implicit language Q-learning is and, looking at the experiments from the paper. Yeah, so implicit language Q-learning builds off of this recently released offline RL method called implicit Q-learning, which is sort of like the state-of-the-art offline RL method in general, I think. And so the setting this implicit Q-learning paper looks at is, the same as what we discussed. We want to learn the optimizing reward, and we have this constraint of no environment interaction. So I'll first see, is there a question in the chat? Has hybrid online-offline approach been considered? For example, maybe start with an offline approach, then use a smaller amount of data to do online RL. That's a great question. And yes, people are working on this. So maybe you have a lot of data, you want to, get a good policy to start with by learning from the data, and then you can like fine tune it with online RL. This is definitely something people are looking at. Yes. At least in the robotics world, like this stuff has been explored more in the robotics and less in language, I think. Yeah, so we'll start by looking at like Q-learning to understand implicit Q-learning. Yeah, so the Q-learning basically, what we're going to see like why we can't just do Q-learning in the offline RL. So Q-learning, we have this notion of a Q function where it measures sort of the expected value of taking an action in a given state and then following a given policy thereafter. So you have sort of, this Q function is with respect to a certain policy. And then the value function, which we'll need for understanding implicit Q-learning, measures sort of the expected value of a given state under a given policy. Q-learning asks sort of this question of,
Adam?
Yep, question?
Sorry, my bad.
Oh, okay. Yeah, so Q-learning asks this question, the Q function is parameterized, it's under a specific policy. Q-learning is like, what if we could find the Q function for the optimal policy? Then we could just act according to that Q function and, take the action that corresponds to the, maximum Q value, and we'd be, acting according to the optimal policy. And it turns out there's a really easy way easy way to find this by finding the Q function that satisfies this Bellman equation. And you can actually, find this Q function by doing some like dynamic programming things. There's a few more tricks, and this is what, DQN tries to do. This doesn't work in the online RL set or offline RL setting generally, because we're taking this maximum over actions on the right side of the Bellman equation, we're considering, every action possible, which might include actions that are totally out of distribution for the data set. And so we have no idea like how to estimate the value of those actions since they're not in our data set. Online RL could just go out and try it and then update, but offline RL, we have no idea. So yeah, we're gonna have like really bad value estimates if we try to do, like DQN on an offline RL data set, unless the data set's like has huge coverage or something. So implicit Q learning sort of recasts this Bellman equation with an additional constraint, which is, we're gonna not just take the maximum over all actions, but take the maximum over all actions that have some probability greater than 0 in the data set. And this sort of fixes the problem. And how we actually do that, find this Bellman equality is by essentially learning a value function, which represents this right-hand side maximum over Q values. So we do the Bellman thing, where like you fit the Q function to the reward plus gamma times the maximum over Q values, which is represented by this value function. So that learns the Q function. And then to learn the value function, you fit the value function to these Q values, to the Q values at that state, with this sort of weird mean squared error thing. And the idea here is that like, it's sort of a lopsided mean squared error, which sort of penalizes the value function for like underestimating values more than it does for overestimating values. So what this does is it incentivizes the value function to estimate the upper expectile of the data set, upper expectile value of the data set, rather than just like the mean value of the data set. And it sort of approximates this maximum thing.
Sorry, I
yeah.
just have one question. In the context of reward, then does that basically mean you're having it focus more on positive rewards over punishments, or is it like you're focusing more on punishments over rewards? That's the effect that this has, isn't it?
Yeah, so I think the way to think about it is this: you have your data distribution. Some of it is positive reward stuff, some of it is negative reward stuff, and the value function is sort of like acting as like a filter over the data set, like an implicit filter where it's like just finding the good stuff in that pile of data. Does that make sense?
But I'm more so just curious of what having this lopsided MSE accomplishes in that regard.
So the lopsided MSE incentivizes the value. So it approximates this maximum over actions under a support constraint. So I think this second plot actually illustrates the idea. So suppose, you have, the value of your states is, on the x-axis, and the probability of that state is on the y-axis. The average, data set policy, if you followed the data set policy, you'd get like, a policy with this value. Whereas if you take sort of find the policy that corresponds to the upper expectile of the data set, you'll get something more on the right side. It's still in distribution, but it's, taking the good stuff that's in distribution,
so
the good
it's
tail.
like optimistic
Yeah.
in a sense.
It's not, usually when RL people talk about optimistic stuff, they're referring to like, you believe that like the action you take will lead to the other person doing something good for you and helping you get your reward.
Yeah, right.
Yeah, that's not what, but it's not optimistic in that sense. It's just like trying to find the good stuff essentially. Yeah.
Okay, gotcha.
Yeah.
Hello.
Hello. Do you have another question?
Yes, I did. So maybe, can you go into this a little bit further? Because I don't understand what exactly you mean by the value function is fitting to the upper expectile of the Q function.
Yes.
And like it sort of also seems a bit like you said, it's sort of penalizing underestimation over more than overestimation.
Yep.
Whereas Q learning is known to have overestimation behaviors in certain settings, right?
Yep.
So why would you do that?
Okay, yep, good question. So actually Q learning is going to overestimate much more than this loss function. And so you see the difference between this max over A and max over A under the data. Since you're considering fewer A's in this case, like it's going to be, you know, less than or equal to this one, right? So the value function is essentially approximating this thing. Yeah, and you're essentially, so in the Bellman equation, like you could imagine standard Q learning would replace this VS here at the bottom equation with like the maximum over A in the next state, which is sort of this dynamic programming thing. But instead of just taking the maximum, we're only taking like the upper expectile of the data set. And this, I keep saying upper expectile. This expectile is controlled by this tau parameter. So if you turn the tau parameter closer to 1, you're getting closer to this hard maximum over actions. And if it's like at 0.5, it's equivalent to the data set policy. Yeah, and you're right that you're still probably going to like overestimate things here. And that problem doesn't entirely go away. You can still do like the tricks like taking the minimum of 2 Q functions and whatnot to, you know, mitigate this. But you still need to take the maximum, because if you don't do like some form of maximum, like in this case, it's an expectile maximum. If you don't do that, you're just learning a policy that represents the data set, which isn't what we want. We want to find, you know, the best policy we can. Yeah, I could, let's see. Let's see if we, yeah, I probably should have written out the like original Q learning Bellman equation here, but really the only difference between them is the original Q learning takes maximum over all actions here, versus ours takes sort of like an upper expectile of actions, which should generally be less than the maximum over all actions.
Okay, yeah, that makes sense. Thank you.
Yeah. Yeah, so that's sort of like the key like idea behind implicit Q learning that we build off of in our work. And so we sort of adapt this algorithm to, you know, language models. I mean, it's pretty straightforward. We do this with essentially 3 transformers. So in, you know, implicit Q learning, you don't actually need to learn pi beta, which is the data set policy, but we do that and we'll get to why. There's 3 transformers. One is this like data set policy, pi beta. So you just your standard supervised learning model. It could be, you know, anything that, you know, is just trained on that data with supervised learning. And then the other is, you know, this IQL value function transformer, which has a value function head and a Q function head, which is trained with the implicit Q learning objective that we just discussed. And then you also need a target Q network, which is like, you know, the same idea as like DQN, where you take a, you know, a polyic average copy, or, you know, a target, basically a delayed target function of the original Q values, and this just stabilizes learning. So I mean, to some degree, there is still a few components going on here, but it is, as we'll discuss, there's some things here that are like more stable than other offline RL approaches.
Pi beta is just a fine-tuned language model?
Yes, pi beta. So when we say pi beta, that's just a fine-tuned language model on the data set. Yep. Yeah, it's an offline RL term.
I'm just kind of curious, like how important is the fine-tuning step? Like have you tried ILQL without fine-tuning first?
Wait, what do you mean?
Like you have to fine-tune on your data set. So you have to fine-tune on like,
oh,
doing a chat, you have to fine-tune on
no,
chat.
so this is slightly different than that. you can do this Q function learning, the value function learning without fine tuning. You just give it the data and do the value function learning. The
Got
pi
it.
beta transformer is like a separate model that represents the supervised policy. You need that for the for inference, which I'll discuss in a second.
Okay.
To get the Q values and value functions, you don't need to do that. Yeah. Yeah.
So relating this back to the thing you were saying about offline RL in theory,
Mhm.
is the pi beta basically that precursor model that you're using to collect transitions?
The pi beta, yeah. So the pi beta represents like, well, not exactly. The pi beta just represents like the policy that's in the data set. So like maybe, you know, you have a data set of like, you're a customer service bot and you have a data set of a bunch of like prior customer service interactions. Pi beta is just like a language model trained on that data to imitate that data. Yeah.
Okay, so in the offline setup, right, the theoretical
Yeah.
setup, when you had the model that you have beforehand that you're using to collect data, what is that model in this context then?
Using to collect data.
In the
Well,
diagram that you had before, it was like the left and the right side, right? There was
let me go back. Were you talking about? Oh man,
that's odd.
you're talking about. Oh, you're talking about this,
Yeah,
right?
that one. Yeah,
Okay,
that one.
so yeah, this is kind of an abstraction. So you don't have to have a model go out and collect your data. What we mean by like pi beta could be, it could be defined by like, suppose you have a bunch of data collected, like random internet Reddit data. You could define pi beta as like, you know, the average of all the humans that were, you know, generating the text. Yeah. So
I get
it's not a
exactly what you mean.
model.
Okay, yeah.
It's not necessarily a model. It's a weird term for defining the data set distribution.
Right,
Yeah.
right. It basically is the
Yeah.
data set because it's, yeah, okay.
Yep.
That makes perfect sense.
Yep.
Yeah,
And
yeah,
so
yeah,
when
yeah.
we say it over here in the later slide, we're just approximating that with a model. Yeah.
Okay. All right, that makes sense.
Yep. Yeah, so that's it literally just means the data set distribution, and offline RL refers to it as pi beta. Okay, so yeah, those are the like three main components that you need to train for implicit Q learning, and we'll see why you need this pi beta transformer in a second. So the reason is this. So when we train our implicit Q learning Q function, actions that are like out of distribution in the data set aren't going to get trained. So if we look here, we're sampling state action pairs from our data set, and then we're updating, you know, the Q function at those state action pairs. If there's like a state action pair that's totally out of distribution, the Q function would have never gotten trained on that, and its value could just be arbitrarily large or something, which could cause, you know, if we're just, you know, looking at the Q function and taking the maximum action, this might cause us to do some weird things. So we need we can't just use the Q function in implicit Q learning. We have to do a special thing to get a policy from that Q function. And so how the implicit Q learning paper does this is they optimize another model to learn this policy. And so what it does is it uses the Q function and value function to reweight the samples in the data, and then just trains this model like with a weighted, it's basically a weighted log likelihood loss. So where like high Q value actions get like a high weight in the loss function, low Q value actions get a low weight in the action. So that's sort of this. And you can control this weight by tuning this beta hyperparameter, which is like a training time hyperparameter. So you can imagine like you might have to try this a few times with different beta to get the best behavior. This isn't super ideal because you have to train another model and you have this beta term to tune. And like if you're, you know, in NLP, like this is just like another complexity to add. So ideally, we'd like to remove this and simplify it. And so we can sort of look at this loss function and see that, you know, the policy it's learning is basically pi beta times this is proportional to the probabilities of pi beta times e raised to the Q minus V times beta. And then, you know, we can rewrite this as, you know, exponential plus, you know, the language model logits perturbed by these value functions essentially. And so, you know, if we just learn the pi beta model, we can literally just extract, you know, the same policy in theory that IQL would get by just perturbing the log probabilities of the language model with the value functions. So it does sort of like what you see in the traditional control generation literature, where, you know, you learn some classifier thing and then you use that to perturb the language model towards, you know, your goal. So we're doing that here with basically an RL setting. And the other good thing about this is that this beta hyperparameter, you can tune to inference time instead of training time, which is a lot easier to do, I think. Yeah. However, unfortunately, this by itself doesn't quite work. We need to add one more thing in order to, you know, get this to work. So like I mentioned, there's this problem where these like actions that are at out of distribution actions can have like arbitrarily large Q values. And then there's also this problem where like the pi beta model that we learn is not going to be perfectly calibrated. It's probably going to be over smoothed, and it won't actually assign a probability of 0 to these out of distribution actions. It will assign a low probability, but not low enough. And so the result is like these out of distribution Q values can occasionally just overpower the language model. And it does some weird, when it does this, it looks like just gibberish that it's generating. So yeah, this is a problem. And there's sort of two ways we can approach fixing this. One is we can either push down the probabilities that these out of distribution actions, or we can push down the Q values at these actions. So in the first case, with the probabilities, we can do this, you know, with standard language model tools like top P filtering, or, you know, tuning a temperature on the logits, which sort of pushes down these low probability actions. And this sort of works. Or if we want to push down the out of distribution Q values, what we would do is when we're training our IQLQ function, we add a small weight on like a negative log likelihood term to the Q values. This is a bit weird. So we're saying, you know, estimate the value of the data, but also push up on the value of actions that are in the data and down on actions that are outside the data. It's a bit weird, but it actually turns out that, you know, one of the most popular offline RL methods, conservative Q learning, this basically does this. Adding this negative log likelihood term is equivalent to conservative Q learning, which is, you know, a theoretically very sound offline RL method for Q learning. So it's entirely valid to do this. It's not just a hack, essentially. And we find that like both of these approaches kind of work in practice. Actually, adding a negative log likelihood term to the loss is generally more reliable, because, you know, if you try to tune the probabilities, you might be doing more inference time tuning. Whereas this negative log likelihood term, you actually don't need to spend much time tuning the weight on it. In our case, we're just using this term to like push down the tail of out of distribution actions. We're not, you know, using it to fix all of the offline RL problems. So you just set it to like a very small weight, and it usually does fine. Yeah. So we do need to add this. And so when we talk about ILQL, we're talking about, you know, the implicit Q learning loss plus a CQL, conservative Q learning negative log likelihood loss term. And so this is sort of the whole training procedure. Okay, so let's see how much time. Oh man, yeah, okay. I'll go through some of this stuff a bit.
Go over a bit.
Okay. I might skip a little bit of details, but yeah. So we have this implicit ILQL method, and as sort of like a first check that it's, you know, ideally, you know, the method is straightforward to tune, and it's got, you know, the, you know, powerful optimization over, you know, a data set. So we want to sort of verify this second bit by, you know, testing it in sort of like a setting where we can really control. So the first thing we'll note about ILQL is that we're essentially fitting our Q values to this like approximate maximum over actions. And when we're doing this, we're sort of like recursively improving the policy. Every time we take the maximum over actions under the current Q value, we're, you know, representing the value of like a better policy. And, you know, we're iteratively doing this. There's what's called like multiple steps of policy improvement. Whereas like more standard or like filtered fine tuning, decision transformer, this other thing in RL called SARSA, do what would be amount to like a single step of policy improvement, which should be strictly worse than multiple steps of policy improvement generally. And so what this is like you're essentially, you know, evaluating the data set policy, and then you're, you know, taking one step of improvement on the data set policy. Our method should be better than this. And we check this in sort of like a controlled setting of Wordle. So we set up sort of this toy data set based on this Wordle game, which sort of looks like dialogue, but we can, you know, more easily evaluate it. So it looks like dialogue in that there's sort of this back and forth where you submit a word and then you get back something from the environment saying like, oh, you guessed wrong here and here, and then you try again. And our model's objective is, of course, to, you know, guess the right word in as few turns as possible. It gets -1 reward each word it submits. So in this Wordle environment, we construct a very specific data set, which sort of tests how well our models can, you know, do multiple steps of policy improvement. And because I'm a little over, I won't go into the details here, and it is a bit detail heavy. So I'll skip those slides, but basically the high level idea is this. We have this like abstract decision process where we have 3 paths. One is from S0 to goal, one is S0 to lava, and one is S0 to S1. If you say you had a data set with one of each of these 3 transitions, if you did a single step of policy improvement, your model would learn to actually just go from S0 to S1, because the value of going S0 to S2 is 0, because these 2 paths cancel out. Whereas, you know, so we'd expect like a SARSA, which is the single step policy improvement method, to go S0 to S1, but ILQL should be able to learn to find, you know, the optimal goal path, which gives you the most reward. We sort of construct a version of this scenario in Wordle. Like the details are all here. Each of these paths is represented by like one distribution of data. The details, you can read the paper or we can discuss it more later. But basically what we see is that like indeed ILQL learns to take this path, whereas, you know, SARSA takes this path in our Wordle game. So that's a good check that, you know, our algorithm is like able to do sort of these more powerful optimization techniques and whatnot. And this isn't just like a special case for the synthetic data set that we created. We also scraped a bunch of Wordle games from Twitter and just trained our models on that data. And we see that, you know, even in this more natural Wordle distribution, our method is better than SARSA and other baselines. So yeah, and the other thing about Wordle is we can compute like it's not optimal, but the policy that selects the word with the highest value of information and get sort of like a very strong upper bound on performance, or not a strict upper bound, but a strong like high performing policy, and we can kind of compare like how close we get to that. But you see there's still some room to improve. Okay, so that's with sort of the toy tasks. Now let's move on to like real dialogue, real language stuff. So now we discussed sort of like the whole point of offline RL is for optimizing over these like interactive settings like dialogue. So let's test our method on a dialogue task. So we do this on like this visual dialogue task, which is we're playing the role of a question asking bot, and the environment has this image that we can't see, and they're supposed to, you know, answer our questions about the image. And our goal is to, you know, ask highly informative questions which can, you know, give us enough information about the image to guess what the image might be. The details about this setup are, you know, are in the paper. I won't go into them, but essentially we have a big data set of this visual dialogue conversations, and we apply 3 different rewards to this data set. One is this, what we call the standard reward, which is at each turn you get like -1 reward. until you're able to guess the correct image, essentially. So you're incentivized for like asking informative questions to gain as much information about the image as quickly as possible. Then there's the yes, no reward, which might be a little bit arbitrary, but we'll see that it like demonstrates an interesting thing about offline neural. So what this does is, in addition to the -1 reward at each term, it also gives you a -2 reward every time you ask a yes, no question, which is determined by like whether the answerer answers your question with an exact string match of yes or no. And then we also include this conservative YN, which is the same as the YN reward, but it doesn't measure yes, no questions by an exact match. It includes more string matching heuristics. Like, for example, you could ask a yes, no question and they could respond with, I don't know, or yes, it is, something that's not an exact string match. So this applies like a more conservative penalty to these kinds of questions. So those are the 3 rewards we evaluate. And we see that like these yes, in the data set, there's a lot of yes, no questions. So this yes, no reward is like highly, the data set is highly suboptimal for this reward function. But, our method is able to find a good policy anyways. It's able to figure this out, despite the fact that, the data set is really not good for this. So under the same data, we can optimize for different things is essentially what this is saying. And we outperform sort of these baselines. We also see as just a check that like optimizing, if we optimize ILQL for one reward function and evaluate it on the others, it's really suboptimal. So, it's learning something different if we train it for one function is essentially what this is saying. That's what this table is showing. Like if we optimize, for the standard reward function, we do really poorly on these yes, no rewards. Whereas, if we optimize for the yes, no one, we're like more specialized to that utility. And then qualitatively, we do see like the yes, no models learn to ask fewer yes, no questions. So it does what we expected essentially. Okay, so now the next experiments we tried was this. So offline RL, an interesting thing about it is that it can sort of optimize things in the face of a lot of noise. So these Q functions are representing like expected values over the data. So it's sort of like averaging out a lot of noise. So we sort of wanted to see like, in NLP, there's a lot of reward functions might be like highly noisy or subjective. Like, for example, given a comment on social media, 2 people might disagree about whether to classify the comment as toxic. So there might be lots of like subjective things in language that result in really noisy reward functions. And so we want to see how well can ILQL optimize these really noisy reward functions. And we test this on, a large data set of 4 million Reddit comments. And we look at 2 different reward functions that sort of have some subjectivity to them. One is this toxicity reward, where we want to incentivize our model to generate, non-toxic comments. It turns out there's a lot of toxic content on the internet. And so, can we train our model to like not imitate the toxic data? And we're using the toxicity filter we're using is OpenAI's like GPT-3 toxicity filter that's on their API. That's the reward function. And then the other one is we want to optimize for comments that get positive upvotes. So we can, because this is offline RL, we can use the actual upvote count in the data set as a reward function. We could also train a model on to predict upvotes and then reapply that. And so we check both of these cases. At evaluation time, we use our model that was trained to predict upvotes as the metric, since we can't go back on Reddit and determine if the model's generated comments would have gotten positive upvotes very easily. So we use like approximation there. And what we see actually is that ILQL gets the maximum possible reward on 2 out of 3 of these settings. So in toxicities, the reward of 0 is actually the highest possible reward. And same with upvotes model, reward of 10 is the highest possible reward. What this means is that the model never generated a toxic comment in our evaluation of like 1,000, we had to generate 1,000 comments. And these comments it's generating are like conditioned on like the parent post in the Reddit thread. Yeah, And this is in contrast to like if we did something more traditional, like filtered the data set for all of the non-toxic comments in the data set and just trained on the non-toxic comments. It turns out that like if you do this, it still occasionally generates a toxic comment, comment that is at least labeled as toxic. So this actually highlights sort of an advantage of offline RL, which is able to like, you know, given a noisy reward, it's able to sort of find the safest possible outputs that like have the highest probability of satisfying it. You can think of it as this, like, suppose, you know, in the data set, there's like some comments that like have a 50% chance of getting labeled as toxic or non-toxic. The filtered fine tuning is going to, you know, accidentally copy these comments that like manage to get labeled as non-toxic, even though they had a 50% chance of getting labeled as toxic. Whereas ILQL, because its Q function is representing an expected value, it can see that like, oh, there's a 50% chance of this comment being labeled as toxic, and it can be like, oh, let's actually do a safer thing than that. We want to maximize our expected reward. So that's an advantage of, you know, offline RL over like just filtering the data and fine tuning on it. So it's more robustly able to optimize these subjective rewards. That's a big point.
I'm kind of curious, and maybe you'll comment on this, but what is the trade-off between optimizing these rewards, but then also experiencing some amount of collapse? So maybe your model just resorts to, you know, the same very positive non-toxic comment over and over.
Yeah, that is a great question. Actually, I don't have that in the slide, but it's in the paper, and that does in fact happen. Actually, I could just pull up this plot from the paper. Hopefully I had the paper pulled up. It's in the appendix. So what happens, you're right, is you know how we have that beta term that we discussed in our ILQL. If you turn the beta term too high, it will literally just learn to find the safest possible comment and just generate that every time. It's like in the in the toxicity case, it's just like thank you or something. It's like kind of objectively, yeah. So it does that. But you can kind of interpolate between like, you know, if you set beta to 0, you're just generating the data policy. If you turn beta all the way up, you're going to be optimizing really hard. And you can kind of interpolate between these two cases. And what we see is that like, so here we measured like the policy's entropy as you turn up the beta value. And, you know, you see like, as you turn it up, the entropy collapses and it gets more and more optimized. But like, there's still a lot of like intermediate points where it's like more diverse than, you know, filtered fine tuning and also more optimal, like right here. Yeah. So you can kind of interpolate between these two and have your pick, I guess. Yeah.
Interesting. So it's like this Pareto frontier of safetiness and diversity.
Yeah, exactly. Yep. Yeah. So I think that was a great question. Yeah, and then the last like result I'll share is like we did some ablations on the visual dialogue task, and we saw like we compared it to a bunch of other offline RL methods here, and we see like, you know, our method is generally outperforming these other methods. We tuned these methods, you know, hopefully I think we tuned them reasonably well. And we also see that our method is generally a bit more stable with respect to hyperparameters, which sort of indicates that, you know, that claim about being a bit easier to use than some of these other methods. Yeah, so I mean, that's all I have. We can have a discussion, ask questions. I'm probably a bit over time, so if people have to go, definitely don't hesitate bouncing. Oh, how did it perform against PPO? Yeah, so I guess we didn't actually compare against PPO because like we're looking at offline RL here and that's online RL. I expect that like, so I guess PPO is not even practical in like the visual dialogue setting because there's an interactive loop. But in the Reddit case, we're just generating comments, so we could have compared it to there. We didn't. I would expect that PPO probably does as good, maybe better, because it's able to sort of interact with the reward function. And I guess the result of that is it might be able to like hack the reward model. But you're right. So like yeah, we didn't compare against it because it's sort of like a different like setting with different assumptions than what we're looking at here. Yeah.
I have a question. Can you hear me?
Yeah.
So first of all, thank you for the great talk. My question is, do you think it's practical to model the value function together with pi beta the way they do in trajectory transformer, and still be able to get this type of of logic re-ranking?
That's a great question. It should definitely be feasible. That's something we didn't do in this paper, but I've explored that a little bit. Like you can definitely use like you can definitely like train the pi beta model, not just to predict your own utterances, but also like what the other person would say. And then you can, do sort of like a planning thing with the ILQL Q function paired with the pi beta model, and just like the trajectory transformer does. And yeah, it should work. I have experimented with that a little bit on like the Wordle task and stuff, and it works pretty well. Yeah.
So in that setting, would we still be needing to perturb the logits, or would we use more of like a dialogue rollouts kind of thing where we just
there's
re-rank?
multiple ways. I guess there's a lot of ways you could do it. Yeah, you could literally just generate rollouts from the model and then re-rank them with like the value functions or something. I think the way the trajectory transformer did it was they used the Q function as like a search heuristic. So like, instead of just naively sampling, you're gonna like sample, the high Q value trajectories more often. So you could still perturb the model when you're doing these rollouts, and that might be better. Yeah.
Cool. Thank you so much.
Mm-hmm.
I think there might be a question in the comments, maybe two.
Okay. I see how this model is outperforming filtered and supervised learning. I think I missed it in the beginning of the talk, but what are the other advantages? I think it's more flexible, but is also more efficient. Yeah, so I guess the main advantage over supervised learning is like you can directly optimize for any utility function you want to place over the data. It has, the advantage of like, being able to handle the noise in the data a bit better. Yeah, I guess those are the main advantages. Yeah. So the main thing is like we want something that can, directly optimize for what we want rather than having to like filter the data set for, optimal behavior or something. And the other question is, what do you think are the biggest model sensitivities here? Example, in your evaluations, were tuning more important for final performance with some hyperparameters over others? Yeah, good question. I think the tau hyperparameter in IQL is pretty important to tune. So sometimes, ideally, if you turn it up, you should get better performance, but sometimes, a more intermediate value works better, and it really depends on the task. So that's one hyperparameter you should probably tune. Yeah, the CQL term doesn't need too much tuning in my experience. Like you can generally like it works for like a lot of reasonably small values. Those are the main hyperparameters, and then the beta term is an inference parameter, which it's inherently easier to tune than training time parameters. So yeah.
What was that first parameter?
Tau. Let me go up to the slide. It's this. Wait, where is it? It's up here. Yeah, it's this parameter. So I did briefly mention this. I should have talked about this a bit more. It's basically, this represents like how lopsided this loss is. So if you turn tau up, it's essentially like a right angle, and it's sort of like the limit. If you turn it up to 1, it's like this right angle, sort of. If you put it at 0.5, it's like a normal mean squared error. And so what this does is like, if you turn it up, you're learning the value function for like a higher expectile in the data set. You're learning like a harder maximum. Whereas if you turn it down to like 0.5, you're just learning like the average in the data. And you can kind of adjust like how hard you're gonna like try to push the maximum in the data set.
Did you find that with some of the different like tasks you looked at, it was more obvious is the wrong word, but like you could kind of intuit whether it was going to need aggressive tuning or not. Like I'm trying to think, like some tasks are very much like it's all types of language. It's like it's basically a general language task, just slightly like distribution shift away from the pre-training, whereas some are like hyper specific.
I think it was, I actually don't have like any obvious like features for how to tune this one. Like, yeah, I think like in my experience, it really kind of was sort of a trial and error thing. Like on these Reddit tasks, you wanted tau to be like 0.6, like barely over, like not optimizing too hard. Whereas like on the Wordle and dialogue tasks, you could turn it up to like 0.9. So yeah, I'm not entirely sure about
but in general, like the success of the policy, or maybe the size of the variance of the policies you got was like pretty highly dependent. Like what did it look like?
Yeah. Okay. Yeah. So the thing you want to look for is just like see if the Q values are like way overestimated. If the Q values during training of the Q function are like way higher than you'd expect, then you should turn down the tau. Yeah.
Roger.
So that's like a straightforward way to like tune it without having to measure the performance all the time.
Yeah, you don't want like that cost saturated. Very cool. Thanks.
Did you look into automating that? Just like automatically saying, oh well, the Q values are too high, therefore I just anneal tau.
I haven't looked at automating that. There's Ilya, the second author on this. He's actually the one who wrote the implicit Q learning paper. He's the main author on that, and he's been trying to figure out these things, like how are you supposed to automatically tune these offline RL methods, because it's kind of hard to do with offline RL because you are assuming that you can't interact with the environment. So like, how do you know it's working or not? Yeah, I think that's a big like open thing to study. Yeah.
So there was a question in the chat, by the way.
Let's see. What is a theoretical benefit of directly getting the utility function? I see that it's not hacky and the proper way of optimizing the language model, but can we use the utility function derived for other problems like composing? I'm okay. Elaborate.
I wasn't exactly sure like what we could do with the actual utility function. So I know that like filtering, like it's an extra layer on top, and like you can really like there's flexibility, but I'm just wondering if there's like some insight that we can gain from the utility function derived or used in different problems. I'm just wondering.
Oh, so you're saying, are you getting at something like you train the model on one utility function and then like try to transfer it to a different one or something?
Yeah.
Okay. Yeah. I think that that's definitely interesting. So you can definitely get like very general utility functions by saying something like this. Given like a prompt of like what the task is supposed to be, maybe your utility function is like, would a human say that, that task was completed successfully? So that's like a utility function that like manages to capture like a lot of tasks.
Okay, more general utility function.
Yeah,
okay,
you can do that. Yeah. In general, I would say like if you had a highly specific utility function and you directly optimize your Q function for it, it's not necessarily true that it will be optimal for another utility function. Yeah.
Thank you.
Any other questions?
That's it. Questions. So it's great having you. I think we all thoroughly enjoyed the talk.
Yeah, thank you guys. I'm glad you enjoyed it. I hope you learned something about offline RL for language.
Right. Yeah, sure. All right. I will I recorded the talk. I'll post it in the Discord. You guys can share around as you wish.
Cool. All right. Thanks, guys.